As you see, sections 7A and 7B are about the chemical changes and the types of chemical reactions. We've talked a lot about the periodic table. We've talked some about what a chemical change is. We'll do that a little bit more today. And then we'll describe what the kinds of chemical reactions are. So here we go. In a chemical reaction, remember, we have a process of changing substances into different substances. And this is your key word right here, different. We get something new out of a chemical change that was not there when we started. So different substances, that's your key that a chemical reaction has occurred. Chemical bonds are broken and the atoms rearranged. Now remember, we also have to talk about balancing equations, and we'll do practice sheets on balancing equations as well. But as those chemical bonds get broken, the atoms rearrange, and we have to start with and end up with exactly the same number of each atom, again, just rearranged. Now, how can we tell a chemical change has occurred? Well, these things don't happen with every chemical change, but these are some of the most common results we get that help indicate a chemical change has occurred. Sound, light, a precipitate, which is a fancy way of saying solid, especially if the reaction didn't start with solids. We might see some bubbles, we'll feel some heat, get a little bit of smoke, a flame, such as dropping sodium in water. You've seen the video clips of that. Some kind of an odor, could be a pleasant one, a not so pleasant one. Color changes and ashes form, especially if it's a combustion reaction where things have burned. But again, these are not guaranteed to happen, but they're good indicators that a chemical change has occurred. Ready? Now, what about these things we call chemical equations? I mentioned balancing just a moment ago. When we do a reaction and we write out the equations, we have to make sure that they balance as we're doing in our practice problems. Balancing shows that the law of conservation of matter works. Matter cannot be created or destroyed, only change form. All right, here's a number I've shown you before, 6.02 times 10 to the 23rd. And many will say 6.022 times 10 to the 23rd. But if we look at just this right here, 6.02, you're looking at 602, and I won't write them all out, but then I have to go to 20 zeros, and that's going to be the end of the number. And that's a lot to write out, and that's, remember, why we deal with scientific notation. And the mole usually refers to atoms and molecules, how many atoms or how many molecules that we're talking about. Now you look at the atomic mass of something like oxygen, I'll round that off to 16. The atomic mass of oxygen, one atom is 16 atomic mass units, but a mole of oxygen atoms is 16 grams. So a mole is this number of atoms or molecules, 6.02 times 10 to the 23rd, and the number you see on the periodic table is for a single atom, but a mole of those atoms or molecules for a compound weighs that same number in grams. So oxygen would be 16 grams when we have a mole of those atoms. We can read the equations in terms of atoms and molecules or in terms of moles. The atomic mass on the periodic table, as I said a moment ago, is also the mass of a mole of atoms and grams. So anytime you see this word mole here, you're talking about this number, 6.02 times 10 to the 23rd. That's 602 and 21 zeros that follows. What you see on the periodic table is for one atom for the mass, or a mole of those atoms measured in grams. Ready? There are 5 kinds of chemical reactions. On this page, we'll just list them. And on the next few pages, we'll detail them a little bit more. One is called the combination. Again, I'll save the description for it for the next page, and the same with the others. Number 2 is called a decomposition. Well, you can kind of figure out just by the words that combination means put things together, and decomposition means break something apart. Single replacement, we'll see in just a few minutes. That single replacement means one atom or ion is changing places. And in a double replacement, we have pairs of atoms or ions trading places. And combustion, something is burning, and that something is typically oxygen. So on this page, we're just listing the 5 kinds of chemical reactions, and now we'll talk about those in a little bit more detail. Ready? Oh, we'll practice each on our worksheets as well. Now ready. Sometimes I forget that bottom line on there. Okay. In a combination, I'll tell you in just a bit what those arrows represent. But in a combination, we have 2 or more substances combined to make one new substance. Now, these could be single atoms, or these could be molecules, such as in a compound, already as a compound coming together. But 2 or more substances combine to make one new substance. And again, they can be single elements, single atoms, or compounds referring to molecules. Now, here are a couple of examples here. This says zinc plus sulfur produces zinc sulfide. Now, you'll see many different words and phrases for the arrow. Produces is one. You can say combine to form, react to make, recombine to form, many different things that the arrow right there represents. But here we see an atom of zinc plus an atom of sulfur. So zinc plus sulfur produces zinc sulfide. And remember the oxidation numbers we've done before, we'd have to make sure those work out as well. So zinc plus sulfur produces zinc sulfide. 2 atoms coming together to make one molecule. And another example, these are, we already have molecules making one new molecule. Carbon dioxide plus water combine to form hydrogen carbonate, also called carbonic acid. Okay, remember this is a polyatomic ion, and even though there isn't another subscript out here, I always put those in parentheses to show you and remind you of what a polyatomic ion is. 2 or more atoms put together that pretend to be one. So this is carbon dioxide and water produce or combine to form carbonic acid. So in combinations, we have 2 or more substances combining to make one. Ready? Decomposition is actually quite the opposite of combination. This is when one substance is breaking down and becoming 2 or more. I guess you could think of it as smaller substances. So it's just a combination turned around. Here we have calcium carbonate. You can see calcium and CO3, that polyatomic ion, already together. Some energy goes in. It may not be exactly the way I'm showing you here, but some energy goes in and splits these atoms apart. And now we get a recombination of a couple of the atoms, giving us 2 or more, could be more than 2 depending on the reaction, but 2 or more different substances. So calcium carbonate decomposes into calcium oxide and carbon dioxide. Or you may have 2 molecules of sodium bicarbonate, which is baking soda, getting decomposed and becoming sodium carbonate plus carbon dioxide plus water. And that's probably water vapor because of the energy and those molecules separating. And remember, we would have to balance as well, and that's why the big 2 right there. Remember, we will have to balance our equations to make sure we start and stop with the exact same numbers of atoms on both sides, just rearranged. But in decomposition, one more time, one substance breaks down into 2 or more. And there you see 2 examples. Ready? In a single replacement, the name pretty much gives away what's going on. One element is going to replace another. Now, when you get used to these, you can start recognizing them pretty easily. In this case, what we have is silver nitrate combined with copper, recombine to form, you got the arrow right there, copper nitrate and silver. Now, before I go any further, I want you to notice something. We have a pair right here, silver and nitrate. And we have a solo all by itself on the left side. It could be solo plus pair, doesn't matter which one's written first. But look, we get a new pair right here and a new guy solo left all alone. And that's going to happen on every single replacement. We have a single and a pair become a new single and a new pair. And again, the single could be written first, then plus the pair. But what's happening here is, notice we got the nitrate staying still, but the silver and the copper are changing places. Hopefully the colors help you see what's going on here. The silver and the copper are switching. So the nitrate has dropped the silver and said hello to the copper. So the silver has replaced, let me say that again, the nitrate has replaced the silver with the copper. The copper replaces the silver, and I like to say, as nitrate's partner. So this bond has been broken. The copper has recombined with the nitrate, and the silver's left all alone, and that's going to happen on single replacement. Here's another example. Magnesium plus hydrogen chloride, or hydrochloric acid. Remember, the 2's will help things balance. But magnesium and hydrochloric acid become magnesium chloride and hydrogen all alone. So once again, we have a single and a pair become a new single and a new pair. Again, it could have been H2 plus MgCl2. Now, what happened? What got replaced? Well, look. Who got left alone and who recombined? The chlorine drops hydrogen, and the hydrogen and the magnesium switch places. The magnesium then hooks up with the chlorine, as you see on this side. And you always have somebody left alone. You started with someone left alone, and somebody new is left alone, and that will happen every time in a single replacement. The magnesium has replaced the hydrogen as chlorine's partner. Single replacement. One element replaces another. Ready? Well, if a single replacement has one partner trade, what do you think a double replacement has? Duh, 2 ionic compounds trade. Now, instead of partners, I use the fancy words here to remind you. Cations and anions. Remember, the cations, those are the metals that become positively charged. Now, it could be a polyatomic ion acting like a metal. And the anions, those are the negatively charged nonmetals. And again, could be a polyatomic ion acting as a nonmetal. All right, here are the examples. Sodium chloride plus silver nitrate become sodium nitrate plus silver chloride. Now look what's happening here. We have 2 ionic compounds trading partners. What happened? In this case, the chlorine and the nitrate simply traded. The sodium is still first, the silver is still second, but again, these 2 have traded places. So we have a trade of partners here. And even if you listen to the words may tell you what's going on also. Sodium chloride plus silver nitrate become sodium nitrate plus silver chloride. We have a trade-off, and notice on both sides you got a pair and a pair, 2 pairs and 2 pairs. So with a double replacement, you're always going to have 2 pairs on both sides, 2 pairs and 2 pairs. Okay, here's another example. Sodium sulfate plus barium chloride become barium sulfate plus sodium chloride. Where's the trade-off? Well, let's take a close look here. The sulfur and the chlorine are staying still this time. Didn't go that time. The sulfate and the chlorine are staying still. The sodium and the barium have traded places. Again, the sodium and the barium have simply traded places and therefore traded partners. Traded cations and anions. All right. Oh, forgot to ask. Were you ready? All right, ready. Combustion. Just like the word says, combustion means something catches on fire or has the ability to, a combustive property. One substance, such as a fuel, will act like a fuel and react with oxygen. Things that catch on fire need oxygen in order to keep on burning. And in a combustion reaction, that's what happens. For example, this isn't the only one, obviously. Natural gas, called methane, burns with oxygen to release carbon dioxide and water vapor. Okay, here's methane gas and oxygen, and remember we have to balance, that's why the big 2's here. But methane and oxygen produce carbon dioxide and water vapor. Okay, with combustion, there's going to be oxygen involved in there. And many times, especially if the other one has hydrogen, we're going to get water vapor, a gas form of water coming off. Heat and light often come from these reactions, but not every time. But heat and light, you saw on that earlier page, can help us determine that a chemical change has occurred. And combustion is one of those. It's actually the fifth one that we're talking about. Ready? And that is all. So how did you react to this lesson? Ha, 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 ha. So now you know what the 5 kinds of chemical reactions are all about. Thank you.